Auxiliary system control and monitoring, ensuring intelligent management of supporting subsystems for reliable compressor operation. Auxiliary control and monitoring. The Turbo Compressor Control System TCCS extends beyond core turbine and compressor logic to provide full automation, protection, and diagnostics for all associated auxiliary systems. These systems are critical to safe and reliable operation and are managed through programmable logic within the unit control panel's UCPs. Functions of auxiliary system integration. Automated startup and shutdown sequences. Each auxiliary is interlocked and sequenced based on turbine and compressor readiness. Devices such as pumps, fans, valves, and heaters are activated in a predefined order to support the main machinery's transitions between operational states. Monitoring of operating conditions. Real-time feedback from auxiliary systems is captured and displayed on the human-machine interface, HMI, and relayed to the distributed control system, DCS. This includes parameters like seal gas pressures and flows, lube oil temperature and pressure, nitrogen buffer systems, filter differential pressures, cooling water status if applicable. Automatic duty standby management. Where redundant auxiliaries, e.g. dual lube oil pumps, are installed, the TCCS automatically initiates the standby unit upon failure of the duty unit, monitors health conditions such as motor status, trip signals, and flow confirmation, raises alarms upon switchover, and logs event history for analysis. Fault-driven protective actions. Any auxiliary equipment malfunction that could compromise compressor safety or operation, such as seal gas supply loss, low oil pressure, or fan failure, will trigger alarms on the UCP, HMI, and DCS. Initiate controlled shutdown of the affected compressor if the failure is critical. Optionally inhibit restart until the condition is cleared or overridden by an operator with appropriate authority level. Local and remote visibility. Operators can view the live status of auxiliaries, valve positions, flow indicators, and fault states from the UCP touchscreen interface, external DCS displays via OPC or Modbus links, maintenance terminals or engineering stations, trend and diagnostic support. Auxiliary system data is logged and trended continuously, enabling proactive detection of deteriorating pump performance, filter clogging trends, oscillations in supply pressure, anomalies in backup activation frequency. Testing and simulation capability. During maintenance or commissioning, auxiliaries can be safely actuated in maintenance mode, bypassing certain interlocks while still preserving critical protections. By integrating auxiliary equipment into the overall automation logic, the TCCS ensures seamless process support, intelligent redundancy handling, and real-time health monitoring, all of which are essential for minimizing unplanned downtime and extending equipment life cycles. TASH, compressor surge prevention and performance management. Dynamic control for surge avoidance, load balancing, and process capacity optimization. Compressor anti-surge control. The Turbo Compressor Control System TCCS provides a dedicated anti-surge control strategy for each compressor stage to prevent surge conditions, rapid flow reversals that can damage machinery and disrupt process stability. This function is embedded within the unit control panels, UCPs, and coordinated centrally through the Common Control Panel, CCP, for multi-train systems. Key elements of anti-surge control. Stage-wise control logic. Each compressor stage is equipped with its own anti-surge controller that continuously monitors suction pressure, discharge pressure, flow rate, gas properties, e.g. molecular weight, compressibility. Dynamic surge limit calculation. The controller calculates the real-time surge limit using thermodynamic relationships, compressor maps, and online gas data. It determines the surge distance from surge, often visualized as a surge margin on the operator interface. Adaptive PID control with feed-forward augmentation. Surge protection is achieved using proportional integral derivative PID control. With an additional open-loop component, the PID controller adjusts the anti-surge valve position based on measured deviations. The feed-forward term opens the valve preemptively during rapid disturbances or load rejection events. Recycle trip, RT logic. When the operating point crosses a predefined RT line closer to the surge line, the controller initiates a forced valve opening, bypassing the normal PID logic to protect the machine. Fallback capability. If any critical sensor, e.g. flow transmitter, fails, the controller automatically switches to a fallback mode using estimated or redundant inputs. Alarms are raised and valve control remains active to ensure surge prevention. Controller decoupling. Logic ensures that anti-surge actions on one stage do not interfere with adjacent stages or parallel compressors. This isolation maintains responsiveness and avoids control conflicts. Startup behavior. During compressor startup, all anti-surge valves are overridden to full open until the compressor reaches minimum stable speed. Control is then smoothly transitioned to active anti-surge logic. Operator visualization. On the HMI, operators can see real-time compressor map with live operating point, surge control line and RT line overlays, current valve position and control margin, alarm states and fallback status. System guarantee. The anti-surge system, including control logic, transmitters, and valves, is engineered to guarantee protection under all operating conditions, including sudden discharge valve closure or upstream disturbances. This robust anti-surge control ensures maximum compressor uptime, minimal process disruptions, and extended mechanical life, even under demanding and variable process conditions. Load sharing and capacity control, balancing demand and surge margin across multi-train compressor systems, load sharing system. In facilities with multiple turbo compressor trains operating in parallel, the Turbo Compressor Control System TCCS incorporates a dedicated load sharing algorithm to ensure optimal distribution of compression effort. The objective is not simply to equalize power output, but to maintain equal proximity to surge for all machines, maximizing system stability and efficiency. Key load sharing control features: surge margin-based load distribution. Instead of balancing on speed or flow alone, the TCCS adjusts each compressor's load based on its distance to surge as calculated by the anti-surge controller. Speed reference coordination. The load sharing controller, located in the Common Control Panel, CCP, sends individual speed set points to each train's turbine governor. These set points are calculated to keep all compressors equally distant from their respective surge lines. Dynamic rebalancing. During changes in plant demand or process disturbances, the TCCS automatically redistributes load, decreasing speed on compressors approaching surge, increasing speed on compressors with more surge margin. This keeps the fleet operating within safe and stable boundaries. Fault tolerance. If a compressor trips or a surge margin sensor fails, the load sharing logic instantly rebalances among remaining trains. Alarm conditions are logged and displayed on the HMI and DCS. Operator visibility and override. Operators can view surge margins, speed set points, and actual speeds of all trains. Override automatic distribution logic during maintenance or troubleshooting with appropriate access level. This load-sharing approach extends surge protection principles to the system level, ensuring energy-efficient and reliable operation of multi-train compressor networks. Capacity performance control. The TCCS provides plant-level capacity control to align compressor performance with process demand. This controller resides in the CCP and operates in conjunction with the load-sharing and anti-surge subsystems to balance throughput, pressure, and machine integrity. Core objectives of capacity performance control: maintain plant suction or discharge pressure. Depending on process requirements, the controller regulates suction pressure, e.g. gas intake systems, discharge pressure, e.g. injection or pipeline export systems, set point management. The pressure set point is typically provided by the Distributed Control System, DCS, based on real-time production needs, tank levels, or downstream valve positions. Speed adjustment as primary control action. To control pressure, the TCCS adjusts the turbine governor's speed reference, which changes compressor output accordingly. Integration with surge protection and load sharing. The performance controller does not operate in isolation. It respects constraints from anti-surge controllers to avoid pushing machines too close to surge. It feeds speed set points into the load sharing algorithm, which then distributes them equitably across trains. Override logic when required. If a suction or discharge pressure approaches a critical limit, the performance controller overrides current set points and initiates corrective action. This might involve reducing compressor speed or opening recycle valves to relieve pressure. Flexibility for different train configurations. Whether compressors are in parallel, series, or hybrid arrangements, the control logic is adaptable. Configuration-specific parameters are defined in the Process Operating and Control Philosophy document and implemented via software blocks within the TCCS. With its ability to regulate system throughput while maintaining safe operating margins, the Capacity Performance Controller ensures tight process control, energy efficiency, and equipment protection under all demand scenarios. Override pressure control and controller decoupling, safeguarding system integrity through hierarchical limits and independent loop architecture. Override pressure control. The Turbo Compressor Control System TCCS includes a configurable override pressure control function to prevent the process from exceeding defined suction or discharge pressure thresholds. This function provides an additional supervisory layer above the main performance controller designed to activate under abnormal conditions. Key features of override pressure control. Unified set point across trains. The override pressure limit is defined as a single common set point, typically entered or adjusted via the Distributed Control System DCS. This ensures that all trains respond uniformly to pressure excursions. Configurable activation threshold. The override controller continuously monitors system pressure. When the measured value exceeds the override set point, it temporarily takes precedence over the normal performance controller. It acts immediately to reduce load and bring the pressure back within acceptable limits. Speed set point override mechanism. The controller sends a revised lower speed reference to each turbine governor, reducing compressor output and system pressure accordingly. Fail-safe integration. The override logic is fail-safe and deterministic, cannot be inhibited during active override conditions. Returns control back to the performance controller automatically once pressure normalizes. Application flexibility. The override function can be configured for discharge pressure override, typical for injection or export systems. Suction pressure override, used where upstream supply fluctuations must be limited. Operator feedback and alerts. When active, the override controller raises an advisory alarm to inform operators. Displays current override status, activation cause, and corrective action in progress. This layer of protection provides essential pressure containment capability, preventing downstream equipment stress, flare activations, or safety trips, especially during fast disturbances or performance controller failures. Controller decoupling. The TCCS is designed with a fully decoupled control architecture, ensuring that individual control loops, such as anti-surge, performance, and load sharing, operate without interference. This strategy is critical for preserving control performance, minimizing oscillations, and avoiding unintended interactions. Decoupling strategy and benefits. Independent loop execution. Each control loop, anti-surge, performance, load sharing, override, executes on its own timer, using its dedicated inputs and outputs. This modularity prevents control lag from propagating across functions, maintains responsiveness even under high system load or network traffic. Anti-surge to performance isolation. Anti-surge valves and performance controllers often act on the same process but have distinct goals. Decoupling ensures anti-surge logic retains control authority near the surge line. Performance logic does not inadvertently push the machine toward unsafe operation. Interstage anti-surge independence. In multi-stage compressors, each stage has its own anti-surge controller. These are decoupled to prevent upstream valve movements from destabilizing downstream stages, allow each stage to maintain its own protection envelope. Train-to-train isolation. In parallel compressor configurations, each UCP operates its own anti-surge and local logic. Load sharing coordination is handled at the CCP level, but anti-surge valves are never influenced by the behavior of adjacent trains. Communication-based synchronization, not control. Controllers exchange status and margin data to inform each other, e.g., load sharing uses surge margin inputs, but direct control actions are kept logically and functionally separate. This decoupling design enables the TCCS to maintain high integrity, fast response, and stable control across all operating conditions, eliminating control loop conflicts and enhancing overall system robustness. Machine Protection System, proactive monitoring and defense against rotating equipment failures. Machine Protection Overview. The Turbo Compressor Control System, TCCS, includes a fully integrated machine protection system, MPS, designed to detect and respond to abnormal conditions in the turbo compressor, turbine, and associated rotating machinery. This protection layer is essential for avoiding catastrophic failure, minimizing damage, and preserving long-term equipment reliability. Core capabilities of the machine protection system. Continuous real-time monitoring. The MPS constantly assesses vibration, displacement, thrust position, and temperature signals across critical components such as compressor bearings and casings, gearboxes, power and gas turbines, system-level integration. Protection logic is embedded within the TCCS but executed independently of process control functions to maintain response speed and functional integrity. Diagnostic data access. Measured values are transmitted to the UCP Human-Machine Interface, HMI, and also made available to the Distributed Control System, DCS. For deeper diagnostics, integration with the Condition Monitoring System, CMS, provides extended data analytics. Trip logic independence. All protection trips are executed via hardwired logic paths within the TCCS, ensuring response even if communication links or processors fail. Serial data for non-critical functions. Monitoring information, e.g., trending, status flags may be transmitted between TCCS subsystems or to external CMS using high-integrity serial protocols without affecting trip actions. Probes and sensors. The TCCS's machine protection system is built on a robust set of industry-grade sensors designed for reliability, sensitivity, and environmental durability. Selection and installation practices are aligned with rotating equipment engineering standards. Sensor types and placement guidelines. Temperature measurement. RTDs, resistance temperature detectors, used for components operating below 400 degrees Celsius. Type K thermocouples, applied for high temperature zones exceeding 400 degrees Celsius. Thrust position monitoring. Dual proximity probes on compressor shafts, gearboxes, power turbines, optional on gas generator if configuration permits. Shaft vibration detection, non-contacting proximity probes on all journal bearings X and Y axes. Where proximity installation is not feasible, e.g. turbine outboard bearings, high-frequency accelerometers are used as substitutes. Casing vibration, accelerometers mounted on the casing in alignment with key structural planes, particularly on the gas generator and compressor casings. Key phasers, at least one key phaser per rotating shaft, excluding ancillaries, used for phase analysis, startup diagnostics, and rotor behavior correlation. Preferred manufacturer, all vibration axial position and acceleration probes are sourced from Bentley, Nevada, or equivalent high-reliability vendors. Diagnostics interface. Sensor outputs are conditioned and routed to protection modules with analog outputs and buffered signals for external diagnostic hookup. This instrumentation network forms the foundational layer for accurate event detection and dynamic analysis of rotating equipment health. UCP display and alarm integration. The TCCS ensures that all machine protection data is clearly visualized, alarmed, and logged through the unit control panel's UCP human-machine interface and distributed to plant-wide systems for coordinated response. Key display features: real-time variable display. Live readings of vibration, axial displacement, and temperature are shown numerically and graphically. Alarm and trip thresholds. Each parameter is configured with pre-alarm levels for early warning, trip thresholds for automatic shutdown, hysteresis and delay settings to avoid nuisance trips. Event trend visualization. Time-based plots help operators observe escalating vibration patterns, bearing temperature trends, deviations across sensor pairs. Trip cause identification. In the event of a protection-triggered shutdown, the HMI presents first out, trip signal, timestamp of event, related parameter values at the moment of trip. Data forwarding to DCS. All alarm conditions and measurement values are transmitted to the DCS, ensuring centralized situational awareness. CMS data handoff. Via serial link or Ethernet OPC interface, detailed data is also passed to the condition monitoring system for long-term diagnostics and predictive analytics. This integration ensures that protection events are not only responded to immediately, but also investigated thoroughly, enabling a continuous improvement loop in asset reliability management.